Great. Thanks, Stephanie. And thank you, everyone, for attending. Hopefully this runs smoothly. This talk that I'm going to give today was first presented at Ken Wibbely's DMEC workshop. And DMEC is the Decennial Mineral Exploration Conference that happens every 10 years in Canada. So it's been in like 67, 77. The last one was 2017. And he runs basically a little yearly workshop at the Prospector and Developers Association in Toronto. And by the way, this is about, I came home from this convention, like this, whatever, the 7th of March, and I was basically sent home and have been working at home since. So the conference, or the workshop, was called The Value Proposition for Geophysics. It's not just discovery. My presentation isn't really only about discovery, and you can decide at the when I'm done if it actually has constituted anything of value to you. What I am going to tell you about is, or present to you as a retrospective trip through my 25 years as a geophysicist, which began just as inversion software was being made available to general practitioners, and I guess I consider myself a general practitioner. At the time, specialists didn't really exist then, and I think this is key unless we mean that geophysicists who could actually interpret raw data. At the time, the people I worked for, if you put a pseudo section of IP in front of them, they could interpret through the pant leg and know where to drill. And I believe that this is unfortunately a skill that we're losing, and I think it's a skill that we should actually work to reacquire. Regardless, we started doing inversions and we started producing smooth models. And actually, we've spent the next 20 or 25 years trying to get rid of smooth models. And this presentation is going to discuss why. So I'm going to talk about the inversion hype cycle. And it's something that I've pulled across from business, but I hope you can see where it makes sense. Then I'm going to talk about a bit about inversion basics, some pitfalls towards pseudogeology. And pseudogeology, on the data side, we need multi-parameter data sets. On the petrophysics, we need statistically relevant data, which is more than just a few hand samples. And on the constraint side, how do we apply these petrophysical measurements to a model? What about boundaries and structures? These are all things that we need to deal with. And then most importantly, I'm going to ask you, this is kind of a rhetorical question, but why have I put the cast of Ratatouille up? And I'll circle back to that at the end. So before I get started, this is a slide I like to show, the project management tire swing. This is still, someone goes to you and they say they want a tire string. So what the customer really wants is in the lower right corner. They just want a tire hanging from a branch on a tree. And these are all the different steps. So the customer doesn't explain it well in the top left. So how the customer explained it, how the project leader understood it. I'm going to let you read these, but some of my favorite are there on the top right. You know, how the business consultant described it. We've got a lounge chair hanging from the tree. Bottom left, this is very relevant, how the project was documented, which is basically it wasn't how the customer was billed for a roller coaster, how it was supported as if the tree was cut down. So what we have really in the very top right is this model, in this case, the susceptibility model. That's what we've been providing to the customers. This is kind of smooth susceptibility model. What we really need to supply to them, and I believe what the customer really needs, is this pseudogeology model, which is in the lower right, where we've not only just given them susceptibility, but we're starting to give them our interpretation of what the rock types were. And I think this is what we need to focus on moving forward. We as geophysicists need to focus more on the customer, because as we can see, there are multiple interpretations to a fairly simple problem statement. So the inversion hype cycle is really I said the business, but it's also, I guess it was originally the technology hype cycle. And it all starts with a technology trigger. And in this case, I think inversions in mineral exploration geophysics really started up in about 1991. Then everyone jumps on the bandwagon, and they think that this is the greatest thing in the world, and we get this peak of inflated expectations, which is basically where we don't understand what we're doing, but everyone thinks it's keen, and we start doing things wrong. Well, no, sorry, I mean, or let me rephrase that. We don't do things wrong, but there were a few very early success stories, which were probably more by fluke. Everybody jumps on, then reality hits, and we fall into what's called the trough of disillusionment. And that was, I think, probably similar to the time of the GFC. So, exploration managers were starting to ask, these inversions, they're not really finding the deposits, the tier 1 deposits that we want. At the same time, the GFC hits, we lose some funding. Anyway, we struggle through that. We have some new young researchers who are addressing these problems with smooth models, who are on the slope of enlightenment. And I think maybe starting last year and this year, we're on what's called the plateau of productivity, which is actually where we need to be. And as you see if we look at this, it's going to be 20 years from the start to where we are today, and we're just starting to be productive, I believe. So the technology trigger, I'm Canadian. I didn't grow up in BC, but I live in Vancouver now, which is where University of British Columbia is based. A lot of the work started at UBC with Doug Oldenburg and his team. They made the first gravity inversion, MAG3D, DC inversions, DCIP2D. So his first consortium, it's now called UBC GIF for the UBC inversion facility, but the first one was called JACI, which stood for the Joint and Cooperative Inversion, Geophysical and Geological Data. And that was a great title and a great goal. What was actually kind of interesting was that at the time, the initial sponsorship didn't do any of that. They were doing one inversion at a time, and there wasn't anything joint or really anything cooperative about it. And that's basically taken this 20 years to get to. But there are the highlights on the left. On the right are the consortium sponsors, and I'm just going to go through these just as an aside because they say I have some time to talk. But many of these companies, many of you may never have heard of. So, of course, BHP still exists. CRA is now Rio Tinto, so they still exist. And Rio Tinto is a member of GIF. Caminco Exploration, I worked for Caminco for a long time. They merged and have been rebranded as Tech Exploration. So Caminco's gone. Falconbridge is gone. In fact, at one point, Falconbridge bought Noranda, and then Falconbridge itself was bought by Xstrata, so they're gone. Hudson Bay Exploration and Development, they were a subsidiary of Anglo American at the time. They've now spun off, but Anglo American is still a sponsor. Excuse me. Inco was bought by Vale. Kennecott was, at the time, Kennecott was actually owned by Rio Tinto, but they've been assimilated into Rio Tinto. So CRA and Kennecott are now Rio Tinto. Newmont still exists. In fact, Newmont, what did they just merge with Goldcorp? Okay, that's fine. Noranda, we've talked about them. Placer Dome is Barrick, and WMC is BHP. So there's been a phenomenal amount of consolidation in the industry in the past 20 years. So now we get to the peak of inflated expectations. This is a really good success story that I'm showing here, and this data was collected by Theo Aravanis, I guess at CRA at the time. He was the former chief geophysicist for Rio Tinto. This is the Century zinc lead deposit in northern Queensland. Yeah, I mean, there's not really much to say. You can see the outline of the body. This was a flat-lying stratabound zinc deposit. You can see a resistivity response, and you can see a chargeability response, and the chargeability response is mimicking the top of the ore body. So this is great, and everyone saw this and thought, okay, fine, this is going to be like shooting fish in a barrel. Of course, so people started doing inversions everywhere, and a lot of inversions don't look like this. I mean, as it turns out, we don't do a lot of surveys over mineral deposits, but nonetheless, people were excited. We did a lot more work. And then things started to fall off the cliff. And why did things start to fall off the cliff? So I'm just going to go back and talk a little bit about inversion basics. And at the start, I'm just going to remind everyone of a famous quote by George Box. He's a statistician. He said that all models are wrong. Some models are useful. We have to remember that the only way you have the exact answer is to have the exact thing. So anything that we're doing that's a model or a proxy for something is never going to be good. So in this simple example, we have 2 data points and 4 unknowns. So the data points are 6 and 2. And the 4 unknowns is this M1, M2, M3, M4. And we have these 2 equations. So we have an under-resolved system of equations. So which model do I choose? And this is where I think geophysicists and inversion geophysicists earn their money. We have to choose from a multiple inversions, which are the ones that we're going to. But as you see, there are lots of different solutions and ways to gauge those solutions. So in the left column, we have 4 models, A, B, C, and D, and each of those values answers those 2 equations, satisfies those 2 data points exactly. And we're not talking about any kind of errors, which in geophysics we have to consider as well. And then we have 4 what we're calling model norms. So the first model norm, that's just L1. And what you're doing is we're just adding up all the answers. So 2, 2, 2, and 2. And when you add them up, that phi m is 8. And then in the second column, we have, well, okay, here, we'll go on the first column. So we have 8, 3.6, 3.5, and on the bottom, we have 2.081. We're calling that the smallest model. In this case, small, meaning minimizing the objective function. So if we were doing an L1 norm, and our basis for choosing the best model, for lack of any other reason to choose it, just the mathematical construct of this model norm, we would choose model D. The second column, where we're taking the square of the model, this is our L2 norm. This is where the smooth model is coming out. L1 norms can be blocky, but L2 norms, because they're statistics and they're squared, they were the ones that were concentrated on first. They're easier to converge, but they do make these smooth kind of blobby models. In this case, we would choose model B. So model B is the smallest. And you see there's a fair difference between model B and model D. And the third model is when we look at the difference between 2 models. So now we're kind of assessing a gradient. And in that case, the smallest model is model A. It happens also to be the flattest model. And in this case, so small is small with respect to the objective function. Flat means with respect to structure. So, of course, that first model where it's 2 across the board has the least structure. So we would choose that one. So again, we need to choose which of these models to present to the geophysicist or to the geologist, our customer. I think the challenges that we've had in the past is that our models take a phenomenally long time to compute, or have in the past, and to converge. We as geophysicists are so proud that when it actually works, we give it to the geologist and they go, great. They take it and they run with it. So that's our problem. Their problem, or in fact, it's probably still our problem because we haven't actually able to explain to them what's going on. But were we to give them 3 models in the past, they just get frustrated because they don't understand the math and they want to know what to drill. And if we give them three models that are completely different, and hopefully they're not completely different, but they're going to wonder what we're doing. So this is a conversation we need to have with the customers so that they understand the product that we're giving them. So what about on the data side? I mentioned before, data are inaccurate, so we have errors. Any model that reproduces those data exactly is guaranteed to be wrong. So the realistic goal is that we are going to find models whose predicted data are consistent with the observational errors. In the past, and one of the easy ways to do this is to use chi-squared statistics. And that's the model side objective function. And the expectation here is that phi d, so we're going to take the observed data, we're going to divide it or subtract the predicted data from the model. Their epsilon is actually there on the data point. We're going to sum all of those. And as it turns out, in this least squared norm, this is where the least squared statistics helps. The expectation is that phi d equals n. It's the number of data. So if anyone has ever run UBC DCIP 2D, it converges when the convergence number gets down to the number of data. The one thing that a lot of people don't know is that that expectation n is with a standard deviation of the square root 2 of n. So again, there's some error and some statistics in that. Even that final model that we give is going to have that kind of built-in standard deviation. So there's like 66% chance that the mismatch between the true model and the observation lies in that range of 1 plus or minus 2n. So that's the other side, and that we need to understand, and somehow we need to be able to convey that to geologists without the use of equations. So the trough of disillusionment. This is a project that I didn't work on it at the time. There was another geologist, Chad Hewson, or geophysicist, sorry. He worked on this, and then I came involved kind of after. But this is chargeability data from Western Turkey. This is kind of a gold deposit. And the top pseudo section is the observed chargeability. On the very bottom is the inverted chargeability. And I always like to show the modeled chargeability, which is the middle panel. And that's showing that our inversion can actually reproduce the data. And we can just look at that visually and say, yes, I mean, the things in the observed section appear in the modeled section. So I'm happy. But the problem with this model is when we look at the inverted chargeability, it is very, very complicated. The question is, does that make geological sense? And the risk here is that you give it to a geologist who doesn't ask if it makes geologic sense, and then just goes and drills something. As it turns out, the geologist said, look, that doesn't make sense. So we redid the inversion. I'm going to ask you to focus on those two data points on the left side.
Joel, can you try use your pointer or the mouse at least?
Sure. Here. Absolutely. Thanks. So I'm going to focus on these two data points here. And the next slide is what happens when I remove those two data points from the inversion. So those are the exact same data with two data points removed. And I'm going to go back to what I had before, this complicated, unrealistic inversion, and this other, more smooth and realistic inversion. And I guess we can ask ourselves, how can that happen? And the simple answer is, that it does. It's what happens in the mathematics. It's when we use math to determine the model. Both of these models have inverted. Of course, one of them is going to be a lot smaller than the other. It's going to be a lot simpler. But they both satisfied the inversion, right? They both converged. I believe in this particular case, if you have bad data points in the center of a pseudo section, those data points have supporting data all the way around. So it's probably easy for the model to kind of smooth through those. But when you have bad data points on the very edge of a model, in this case, there's no further data to the left. So there's nothing to support those. And the errors caused by those two data points obviously propagated well into the center of the model. So this is something that we really have to take care of. And maybe if you're doing a very good job, we need to experiment more with how we assign errors, look at Z-scores, which I'm not going to get into, and run different models with different normalizations. Because at the end, when I talked about those different norms, the core of the model that is well supported, it should be identified, I think, by every inversion that we run. And the changes are going to happen, excuse me, on the edges and not in the center. So then we got on the slope of enlightenment, which I think began in a PhD thesis by Nick Williams in 2009 at UBC, and he did a forward modeling study. So Nick is a geologist who went into the geophysics inversion group at UBC, and I think was probably the first person to really ground them on the inside so that they could actually understand, you know, what the customer wanted. So Nick did a forward modeling study, and there's a true density model in that top panel. And basically, he added constraints in a series. Well, he just gradually added more and more constraints, and he did an inversion. So in this case, he took in this first panel, he took that data model, the true density model, he forward modeled it, and he inverted it, and just unconstrained. And that's what we have in the second panel. That's the unconstrained inversion of the forward model of the density model. Then he basically added some surface constraints. So in this case, he told the inversion something about the surface, kind of its depth and its density. And as we see, we get a much better inversion compared to the true data. It's not perfect, but it's good, or it's getting better. Now he's gone and added some more information about the basement. Maybe he said here on the left, he gave on the left side, he gave the kind of the background basement resistivity of this green color, and on the right side, more of this kind of bluish color. Then he added one borehole, and we can see that we basically defined this one part of the deposit a bit better, or the ore body. And then he added two boreholes. So I guess a question that I'm going to ask, and I can't hear anyone, so I'll give the answer too, but which of these constraints, which of these series of constraints has added the most value to the model? I'll pause for a second while you think of it. Okay, that's long enough. If you ask me, the constraint that has offered the most value is the surface constraints. It's the one that I think has done the best job making the inversion look more like the true model. And of course, these other constraints are incrementally better, but this is the biggest change. And borehole constraints to me are very sexy, but if we think about a mag model, or even a model like this that might have 500 cells in it, or 1,000 cells, the actual borehole probably touches about 20 of them. So it's able to impact 20 of those cells and maybe some surrounding ones, whereas the surface constraints are going to impact a couple of hundred cells. And because the surface is the area of the ground that's closest to the sensor, it's what the sensor is most sensitive to. So if we can do a better job helping the inversion out, it does a much better focusing at what's going on at depth, which is what we're interested in. So anyway, so this was what Nick showed, and I thought it was really great. And to that point, I think we're only at the stage now where we have easy tools, or the tools are at least getting simpler to be able to routinely include surface constraints, which is basically be just looking at a geology map, you know, throwing in some outcrops or some densities, approximating depth of cover, and throwing in some susceptibilities or densities. So that's what I was trying to say. I highlighted surface constraints as adding the most value. So the other aspect of the slope of enlightenment is that we've done a lot more to explore the model space, and I've already discussed these norms. But the first one is the L2, which gives which gives a small. We look for the smallest. On the second one, that's a derivative, so that's the structure. We're looking for the flattest. On the third one, we're not only multiplying or normalizing trying to minimize the model. Here we're trying to minimize the difference between the model M, our inverted model M, and the reference model. So in this case, we're trying to make it small with respect to a reference model. And then the last one, we're trying to make it small with respect to the model, and we're trying to make it flat with respect to the reference model. And then there were variations of these on the exponents. There are L1, L2, you can do L1.5, do whatever, L1/2. We now have the tools to play around with these. And I believe what we have to start to do is give geologists, if not give them, we have to show them what the bounds are in the model so that they can better understand the uncertainties in the interpretation.
Joel, can I interrupt you there? I've got some general questions. I'll leave those to the end, but there was a question asked now that I thought it was a good time. So it says, does the order that the constraints are imposed matter to the final model? I know that's more related, yeah, to that slide.
Yeah. Okay, no, that's a good question. I don't believe so. I mean, in this case, Nick imposed these constraints one at a time to illustrate a point. But in the end, all the constraints are thrown into the objective function at the same time. So it all comes out in the wash. It's one big thing and the math just deals with it. So if you want to understand how additional constraints are affecting it, yeah, you throw them in one at a time. It would be interesting to see if you threw in one borehole before you threw in surface constraints. And I think what would maybe happen is we would get a bit more definition on A, but we would lose all this definition on the cover. Now, the thing is that the definition of the cover actually helps focus some of the things that are happening at depth. So it's if you don't impose them all at once, yeah, I mean, you're going to get some sort of hybrid. And I guess I really don't know. So I would say start with them incrementally. Of course, that takes more time. Does
okay,
that hopefully that helps?
Hopefully it answers the question. If not, please post again.
Yeah. Please post again. And sure, if anyone, keep posting your questions. If Stephanie sees something, she can interrupt, and I'm happy to take questions during the talk. So on the petrophysics side, if we are going to provide better models that are more than just mathematically constrained, we need to impose constraints. I think we've just illustrated that. So what kind of constraints? Well, first constraints on the physical properties, and then constraints on the geology. Do we know the depth of cover? Do we have any idea about the geographic locations about certain units? On the petrophysics side, this is what we have our geologists care about: texture, lithology, stratigraphy. You know, geophysicists, on the other hand, are going to care about these physical properties. Right? As it turns out, each rock will have a distinct petrophysical fingerprint. So sulfides typically have high density, high susceptibility often, high conductivity, high chargeability. Granites will have moderate density, could have low susceptibility, unless it has magnetite in it. Low conductivity, low chargeability. So a granite, fine. I mean, I think the moderate density, the low conductivity, the low chargeability are pretty certain. The susceptibility can change of the granite. Interestingly, so of a fresh granite, the susceptibility can vary. The conductivity and the chargeability of a granite will change as that rock becomes altered. And this is very important if we're looking for porphyries, where alteration causes clay alteration, and clays are generally conductive and they can be chargeable. So this is where it's really important to have discussions with the geologist. And it's important to have physical property samples. So we want physical properties of fresh granite, of altered granite, all the different kinds of altered granite. And again, it's not just one physical property per sample, because there's going to be a range, and we really need to understand the statistical variation. But if anything, high and low, even just the bounds of what these physical properties can be. The one thing I'll say is, obviously, we don't refer to the conductivity of granites. We refer to the resistivity of granites, and we have meters that can test the resistivity. But we also have to remember that when we put a sample of core in our meter, we are testing that rock. But when we are doing a geophysical survey in the field, we are measuring the apparent resistivity of the volume of rock. That includes the water in that rock, any fractures that are short-circuiting it. So I think it is still a challenge how we, on the resistivity side, how we take resistivity values and put them in a model. Again, because the values that we measure in the lab don't reflect the rock mass that we measure in the field. But if we know things, and if we start to have two properties to distinguish rocks, in this case, we could have density and susceptibility being property 1 and property 2. And if we have enough samples, we can start to separate the samples and create this kind of pseudogeology. So the geologist would have a name for rock 1, rock 2, and rock 3. We as geophysicists, we can't quite do that, but we can at least say high density, high susceptibility, high density, low susceptibility, and come up with a schematic like this. And we can then take this in our inversions, and actually, instead of just giving them a blob, saying, well, look, these are regions. These are where I think the rocks vary. So towards pseudogeology, there's been some good work done by Jeremy Giroux at the University of Western Australia, and this is from his PhD thesis in 2018. He undertook a probabilistic kind of Monte Carlo uncertainty estimation. So he has geology data, which has some uncertainty, and then on the side he had petrophysical measurements, and he basically took the geological data, the petrophysical measurements, and the geological data sets, and he threw them into an inversion using Monte Carlo simulation, and he came out with an inverted model. So that's what that's what his density model, this obviously like a sedimentary environment, looked like. And after his Monte Carlo simulations, you see that he could actually go and successfully recover most of those geological units to I'd say a highly successful degree. So I think this is good work. Again, to do this kind of work, you have to have lots of physical properties and kind of a reasonable starting model. So another question I'm going to put out there, and I'm still struggling with it, is a lot of these examples are in the data-rich environment, which happens when we've kind of already found what we're looking for and we're trying to refine it. When we're in the greenfield space, doing grassroots exploration, it's a lot more difficult to do this. We may not have a borehole. And in that case, I guess right now my answer is to revert to the surface constraints. At least get as much data as you can out of that surface map. So more recently, Thibaut Astic he's going to defend his PhD, I think in June or July. He's done something similar. He's also done a probabilistic, but not a Monte Carlo method. What he basically does that's different from what Jeremy does is he takes geological data, petrophysical data, geological data, he inverts them independently. And then he kind of cycles through those inversions and uses one to tune the other. So Jeremy took all 3 data sets and threw them into one objective function and came out with an answer using Monte Carlo simulations. Thibault throws them in all separately, and it has some advantages because one tunes the other. Of course, it probably has some disadvantages as well, which I'll probably learn as I start to use it more, because of course there's no smoking gun. But his here number 2, so he uses this Gaussian mixture model, and which assumes that most physical properties are going to be Gaussian distributed. I think for something like resistivity, that's certainly true. For susceptibility, it's probably more log normal. Log normal really complicates the math. But this is where we're at now. So
I have a question, Joel. Maybe we can put it in here. It says, could you comment on the uncertainty in the geological knowledge? What is the best method for quantifying geological certainty or uncertainty?
Yeah, that's a very good question. And when I find out the answer to that, maybe I'll present on that as well. You're right. I think on the geological side, the uncertainty is going to be where the boundaries are, especially for things at depth. When we're looking under cover, we don't have decent maps. A geologist will draw a schematic cross section. I think what we need to do is when they draw their schematic cross section, we need to ask them, well, what is another cross section that could exist that could be equally valid? What if there was a fault here? Or what if there's a fold here? Now, we might have a mag map, which is going to either suggest or not suggest that there's a fault there. But I think we need to use the data that we have. And again, I think a surface mag map and surface geology we should be using those to inform these geological interpretations off the bat. And this is one of these skills, right? Where I think in the people I learned from, they were very adept at looking at a mag map and really starting to picture what was going on, because they didn't have an inversion, so they had to do that inversion in their head. They didn't have computers. So yeah, I think the geology inversion, the geology uncertainty is going to come out through having a sit-down discussion with the project people involved and trying to understand what the possible realistic end members are.
Okay, cool. Thanks.
Okay, so here we have on the left, so we have this petrophysical data across the bottom. This is a classical inversion with a smooth result. We get these Gaussian-like distributions on the density and the susceptibility. But what is shown, all the black dots are the values in the model. So it's a very smooth model, and they're all kind of, this is from a kimberlite. So they're basically all skewed towards the background density. And of course, we get a huge variation in density, which doesn't really make sense, right? We have kimberlites intruding in granites, and we should really have more of a bimodal distribution. So on the right side, we have this petrophysically constrained geological inversion. And here we have some clustered results, and this makes a lot more sense. We have a pyroclastic and a volcaniclastic kimberlite being well represented, or wasn't represented before. We have the hypabyssal kimberlite is again fairly well represented, and the background is, I mean, it's incredibly tight as we would expect, but not nearly as smooth. So I think this is just kind of some sort of 2D representation of this data, but I think it's easy to accept that submitting the right one to a geologist would be much more accepted than the left one. So this is, we're starting to have these toolkits. This code hasn't actually been released to the excuse me, to the public yet, but it's I mean, it's going to be coming out in the domain to those who sponsored the data pretty soon. And I'd say with open source things, everyone's probably going to have access to it within I'm going to guess something like 5 years or so. but don't quote me on that. So that data came from a kimberlite in the Northwest Territories of Canada called, well, it was initially called DO27 and DO18. It's actually called PLATEAU, which I like saying this. PLATEAU in dog rib, which is the local language, means dog's balls. And that's because when this was first flown with the helicopter survey, these two pipes, especially the conductivity, there were these two huge anomalies, and the geophysicists at the time said, holy smokes, those stand out like dog's balls. So this is where PLATEAU came from.
I feel you need someone to laugh in this moment. I'm laughing.
Okay, thank you very much. So this is actually some work that I did because I was involved with this, not during the discovery, but it was discovered in the early, probably about 1992. We didn't have inversions then, but later on when I was with Kennecott, it was a good kind of internal case study. So I did separate density, mag sus, and conductivity inversions, and you can see the plan views or plan view kind of representation on the left, and on the right we have 3D, and you can see my smooth models, and then you can actually, and there are some, some sections, and yeah, so there's my conductivity model, sorry, my mag sus model, my density model. So this was pretty good at the time. I was pretty impressed. Thibault, in fact, UBC has picked up on this again, and he's been using it to run his model. So whereas mine would have obviously been down here, much more smooth, he's able to differentiate between these different sets. Now, in this case, what he's done is post-inversion clustering. So he's run separate models of density and susceptibility, and then he's sort of done almost principal component analysis after the fact, and he's come up with this. We see that this unit here, this red unit, is still fairly smooth, as is the yellow. So in this case, he actually did a true joint inversion where he threw the gravity and the mag data in at the same time, and minimized those objective functions all at once, and came up with this. So I'll just go back to the other one. We can see what's going on here in the PK. There's this kind of maroon unit and this black unit in the background is kind of split up. So there's something going on, but when we look in this case, we get much more favorable clustering. And I think eventually they will add conductivity into the joint inversion as well. So that's probably going to be a next step, maybe a postdoc or something. So we can see that, I mean, hopefully it's clear that this style of data and interpretation would be much better. Now, again, if this was a grassroots case, we wouldn't necessarily have this definition of the ore body, and we may not have that many holes. So one of the things I've actually asked Thibault to do was start to take data out of his inversion, throw in less constraints, and let's find out what the minimum level of geological input and petrophysical input we need to give something that's reasonable, sort of to give us that surface constraint improvement that we saw in Nick Williams' thesis. So we're coming out, this is pretty much the last slide, staying productive. I think it's going to be a combination of technology and workflow. I think we have to, I've got stop the vicious cycle, which is basically we have to stop throwing out unconstrained inversions. Some of you who work for Anglo or De Beers were at an internal workshop that we hosted last year, just north of Joburg, and I think at that time I said I would like to make unconstrained inversions illegal. I mean, there is absolutely no reason why we cannot add some information to our models, and believe that anywhere where we collect data, we have a surface map. And even if it's just to separate cover from outcrop, and then we put in an estimate for cover. So we probably know for certain that the cover is going to be at least 10 meters deep. So we tell the model, you know, this cover is going to have zero susceptibility for 10 meters, and then it could be 100 meters deep. So we can give it a bit of weighting. Like maybe I think I'm 100% confident that it's 10 meters deep. So we give it a susceptibility, and the model can vary from that. And as we get deeper, our expectation of whether it's cover or not is becomes less certain. So we throw in less certainty in our weighting. So it could be weighted 1 on the surface, and down 100 meters it's weighted 0, and then we have some sort of linear gradient. All these things can help the model. So we have to consider the value of information proposition. I think what we really want to achieve is this kind of common Earth model where every cell or voxel is going to be populated with physical properties, geology, geochemistry, if we have it, alteration. Here I have rephrased the question, geophysics as a condemnation tool. I often find we've been doing inversions to try and find the anomaly, which I think is an admirable goal, but we all know that we get a lot of false positives. I think we could rephrase the question and say, well, look, and especially if a company goes and stakes a large area of ground, they typically don't have the human resources to explore all of that. So what we need to do is focus is remove the area that is unprospective. And then so that we can focus our resources on what is prospective. And to me, this is kind of like wine or art. I think people can agree or can agree to disagree. Someone likes a Merlot, someone likes a Cab, someone likes a Shiraz. That's fine. Everyone has their personal taste about what they like, but everyone should be able to agree on what's crap. So I think this is how the geophysics as a condemnation tool comes through. So what's required? I think we need high quality survey collected at the right resolution. We need geological constraints at a minimum, at an absolute minimum, surface geology. I say it again, unconstrained inversions need to stop. We need statistically significant petrophysical data, which basically means collecting borehole physical properties. And we need trained practitioners, which circles back to the start, why I put up the cast of Ratatouille. You know, the fact that anyone can invert doesn't mean that everyone should invert. And that's my talk. A few acknowledgements from UBC. Yep, a few acknowledgements from UBC. Chad Hewson from Tech, Nick Williams from Barrick, Thibault, Dominique, Jeremy, and the cast of Ratatouille. Now I'm done.
Thanks very much, Joel. That was very interesting. I did wonder how the Ratatouille came about. So we have a very interesting question starting out about fieldwork. So the original question came back quite near the beginning of the talk, and I decided to leave it to the end, saying how important is fieldwork going to be in the future? And then it got updated by the end of the talk saying, if most new ore discoveries are deep, is fieldwork then a technical proposition? I'm not sure I understand that. Back to the fieldwork question. If most new ore discoveries are deep, is fieldwork then a technical proposition? Sorry.
Yeah.
Do you want to take
Okay. That? Sure. I'll do my best. And yeah, I mean, to me, the most important thing we do is fieldwork. I mean, they are our observations. And if our observations are poorly made, then everything else that comes from it is poor. And you know, I talked earlier about having one inversion that we send to the project team. I mean, we have to, we have to make good observations, we have to make good interpretations, but we have to make sure that our interpretations don't get confused with observations, because they're not the same thing, right? Our model is never fact, and it's always wrong, and we can improve it. but I think this whole getting people to go in the data or to go in the field and collect good data is absolutely important. I think some companies, there's a movement in our industry that new hires are going to be the best educated people around, and often we're hiring PhDs. But we're all individuals. Everyone has their own skill set, and what we really need is to have a subset of our workforce have to be people who are willing to go into the field. Spend weeks not insist on coming home every weekend from the middle of nowhere. To really have that passion, because deposits are not found in an office. Deposits are found in the field through mapping and drilling. So I hope that answers the question. I think field work is incredibly important, and we need to have good people collecting data, or good people collecting good data. Let's put it that way.
An interesting response, and I think we're struggling with many students coming out of academia that they don't want to go into the field, at least the geology students, so it might be a struggle going forward. I think those people who are willing to go into the field and be good at what they do are going to be a rare and expensive commodity moving forward. A well-paid commodity. Okay, I think you might convince him then. Okay, from Anonymous, it says, is it too late for us to take the geologists with us on this journey, I assume of inversions, based on where we are in the cycle, so they may be able to work with 2 or 3 geophysical models in the future, especially for green fields where we're not certain of what the geology is to begin with? So can we rebuild this relationship with geologists?
I think we can, but more importantly, I don't think we have a choice. A lot of the I'll say the old school geologists who in the 90s, in the early 2000s became disillusioned. They're kind of gone now. They're retired. So we do certainly have an opportunity with the younger geologists coming through. I think we need to do a better job. I mean, I apologize for throwing up some equations. I really think that we should be able to explain what we're trying to do, without equations. I think it was Richard Feynman said, if you can't explain something to a first-year student, then you don't understand it yourself. So I'll just kind of move that into equations. I think with the type of problems that we deal with, we should be able to explain in words what we're trying to achieve, and not, confuddle things by throwing in math and talking about norms. We need to respect our audience.
Yeah, Mark Gerard, I don't know if I pronounced that correctly, says, yeah, it's nice to see the multidisciplinary element coming through very well. No silos. Thanks for the talk. And seeing that in academia as well, you have to be able to relate to people in different fields of science so that you can actually improve on your projects. So there's another question. How far are we from using mineralogical information extracted from hyperspectral information into constrained inversions?
It's probably something that we're looking at. I'd say that we're still, I wouldn't say that we're close. I mean, we're in the very early stages. I guess the trick, of course, is with geophysics, we respond to physical properties. So at the end of the day, we would need to find a link between that hyperspectral mineralogy and physical property. So we might say, well, certain minerals, I mean, in Thibault's example, or in that pseudogeology example, we're going to be, I think hyperspectral data is going to provide much more mineralogical richness than geophysics has the resolution to resolve. But that doesn't mean it's not important, and we'll be able to help inform, if not the inversion, the interpretation of the inversion. And I think, I mean, as we get better with things along the lines of artificial intelligence and machine learning. I think that's going to start to happen, and it will be done, and I guess remains to be seen how useful it actually is. But I think it's certainly something worth researching and exploring, and we are.
Okay, Stéphane's Duplessis just had a comment for our earlier question about is fieldwork going to be necessary going forward. So he said undercover, no real need for fieldwork, but drilling stratigraphic holes will be very important. So thanks for that, Stéphane. From Anonymous, are you a proponent of aiming smooth geophysical models or increasing model roughness to get more rough models? In the strictest sense, geophysical responses are volumetric responses, which would suggest we should aim for smooth models. Are you okay with that? Should I read it again?
Yeah. No, I'm okay with that. I'm going to dissent. I think that geology itself often isn't smooth. And I don't think that our customers, the geologists, want smooth models. They want pseudogeology, which to me implies a bit of blockiness. But again, we have all these different inversion norms and constraints, and we can control the degree of blockiness. And it's going to be work on our part to fiddle around with norms, because we can make models that are small with respect to a reference model, but have sharp boundaries, or we can make them flat. So I think we need to add in data, add in constraints, and any kind of constraint that we put in is going to automatically make our model blockier. So the smoothest model we have is an L2 norm with no constraints. Anything we do is going to make it blocky. So I think we need blocky.
Okay. I was going to say there's one more question, but we've just had another one added. Exploration undercover. Okay, wait, let me read the first one that I've actually practiced reading. Okay, this is from Oleg. What is the current focus area for UBC GIF code development, and where to in the near future? Thanks, Oleg.
Yeah, thanks, Oleg. Well, look, at UBC GIF, Doug Oldenburg is retiring, so UBC GIF is sort of continuing, but a lot of the cognoscenti from UBC GIF are starting to work for Mira Geoscience, who, do the mining suite for GoCAD and Geoscience Analyst. So I think the work forward is going to be, there's two things that they're doing. They're starting to make things kind of open source, and I believe when Dominique Fournier, when Rio Tinto and Anglo brought Dominique to South Africa last spring, Dominique Fournier gave a SAGA talk on SIMPEG, right, which is the kind of open source geophysical inversion. So a lot of these tools are being put online. Of course, you need to know how to use Python, and it's not super simple. But that's one key aspect, things going online. And the other side, Oleg, I think, is the work that Thibault is doing, trying to improve how to make these pseudogeology petrophysically constrained inversions, adding in, I think key things I'll say again are going to be adding in EMs so that you actually are inverting for mag density or susceptibility density and conductivity all at the same time, which is not right now. And I think we need to do a lot more inversion, trying to understand what's the minimum amount of data that's required to give a useful model.
Okay, then officially the last question, and I think it comes back to what you said of so many of these inversions are on deposits where you know what is there. So Tongasai, I hope I pronounced that correctly, said he does a lot of exploration undercover, and I do a lot of unconstrained inversions, and the geologists use that to make 3D geological models. Are we doing something seriously wrong?
Well, I think you're doing, I hesitate that you're doing something seriously wrong, and I'm going to say that you're probably doing the best you can with the tools you have at your disposal. But I do think that there's room for improvement. And again, if something is undercover, we really don't, know what's going on. But you could, if there's some water wells, for instance, in this area undercover, those water wells may or may not intersect bedrock. But even if they don't intersect bedrock, they still give you a minimum depth for bedrock. So that is a constraint. You could say, I don't know how deep the cover is, but I do know that it is at least this deep, and you could throw that into your model. And I'm going to guarantee that if you throw some surface constraints in, because I've done enough of these, if you throw some surface constraints in, it will focus your unconstrained body at depth will be more focused. It will be less, it'll sort of be less smooth, more compact. And why? It's because if this is, for instance, a density inversion, if you know that the cover is, for instance, 2.2, and you have 100 meters of it, the density anomaly that you have will be stronger below that cover. If you don't put in the cover, you know that the smooth inversion is going to allow that density anomaly to bleed into the cover. So you're now going to have density in the cover that is 2.4 or whatever number. You know that's not wrong. So that gets focused in. So my suggestion is to try to put in as much information as you have. And that's the best that you can do. I mean, you can't put in what you don't have. That makes sense.
Well said. Oh, I moved it. Oh, I posted it a while back. So Mary, I'm not sure if you know Mary, who's on the SAGA committee, she's officially quoting you as saying it should be illegal to do inversions without any constraints, Joel. So that might come up in the future with your name next to it. Well, I just wanted to say a huge thank you, Joel, for giving up your time to do the presentation today. And thank you, everyone, for the great questions and the interaction. I really appreciate it. Thanks to Oleg and Brad. I'm not sure which one of them convinced you to do the talk. I hope they pay you in beer or wine sometime in the distant future. Thanks to Wits for this platform to be able to communicate with everyone. I hope everyone found it easy to use. And Joel, I'm not sure, will this talk be posted on YouTube? Were you happy for us to share it on the SAGA YouTube channel? Or is there sensitive data?
No, absolutely. I mean, I think everyone probably could have saved it and watched it on DMAC. And actually, I didn't say, I think the BCGS might have it posted too. So, of course, this is nice. The best one of all.
Okay. Okay, well, so if you've missed anything you want to watch it again, please go back to the YouTube channel. But thanks, everyone. It was great. We had, I think, 33 people attending at the busiest point, which is way more than we usually have at SAGA Talks. So it was great to have everyone. Have a good weekend. If you're from South Africa, I think Monday will be a new normal for us as we move to level 3. Just stay safe and look after yourself. Okay, I'm going to end the event. Thanks again, Joel.
Okay, thank you very much.